Welcome to this lesson of elementary signals. Suppose you want to describe in the signal domain a device which is a switch that can be on or off. So you have this situation, and you can say that when the device is off, you have a signal which is 0. When the device is on, you have a signal which is 1. This elementary signal exists, called step, and it goes from 0 to 1 at time equals 0. If you want to delay the signal to a different time, you simply can write t minus tau. Another kind of elementary signal is used to represent some observations. Suppose you have a ball on a billiard mat and you want to describe the velocity of this ball during the rolling. So due to the friction, the velocity of this ball will go down like an exponential, a real exponential. And this elementary signal, this real exponential, it explains many physical processes. So in general, the elementary signals are used in two ways. One way is to represent some kind of device or some kind of observation. The other way is to use elementary signals to compose complicated signals. So you have the possibility to mix elementary signals so that you can obtain complicated signals. Let's see another elementary signal, which is the constant, very simple. The other one is a rectangle. A rectangle is going from 0 to 1 from minus 0.5 to 0.5. And you can have also the triangle, which is going from 0 to 1 like a triangular shape. And you can have the rectangle, but in this case you are trying to reduce the duration of the rectangle and amplify the amplitude so that it maintains the area. So if you push this process to the limit, you can define a new signal, an elementary signal, that goes to infinity in a time which is infinitesimal, but conserving the area which is 1. So this kind of signal is called impulse and is represented in this way, like an arrow, and the number close to the arrow is telling the area of the impulse. So this impulse is important in many mathematical derivations, and one of them is the properties of what happens if you multiply a function by a signal by an impulse. So you have 0 everywhere unless where you have the impulse. So the product of a signal for an impulse is again an impulse whose area is the value of the signal in the position of the impulse. This relation, this property is written in here. If you have the impulse in a different position, in time equal tau, you have the same derivation, but now the position of the impulse is tau, and the area of the impulse is the area of the function computed for t equal tau. If you do the integral of these properties, you get the area of the impulse remaining in the position tau or t. And if you do another step again, and you do a change of variables from t to m, from tau to t, from m to tau, you get an expression that is this one, which is saying that any signal x of t can be seen like a decomposition of many impulses. These impulses happen everywhere along the tau axis, and every one of these impulses has an area which is the function computed in the position of the impulse. So this kind of writing is a mathematical representation of the decomposition of a signal like a series of impulses. This will be important when defining systems. Now we are going to another very elementary signal, which is the sinusoid. It's a periodic signal. It is defined by 3 numbers: the amplitude of the sinusoid, the frequency of the sinusoid, which is how many periods it has in 1 second, and the initial phase, which is the phase of the sinusoid for time equals 0. You have here one example. So 5 is the amplitude, and in fact the sinusoid is going from -5 to +5. 2 is the frequency, and you have 2 cycles from 0 to 1, and -π/4 is the initial phase, and you can see this happening at time equals 0. I want to show you briefly also what happens if you delay some sinusoids. So delaying the sinusoid is like changing the phase, and what happens is that if you have many sinusoids at different frequencies and you put the same delay to all of them, so you can think of this signal which is the summation of them, you have that for each sinusoid you are removing a number of cycles which is proportional to the frequency of the sinusoid. So the delay converts to a phase modification, and for a given delay this phase modification is a function of the frequency. What happens if we hear a sinusoid? So we are here looking at three kinds of sinusoids. One is at frequency 400 Hertz. You hear the frequency 400 Hertz. Then here is 800 Hertz. And here is 1600 Hertz. So the signal becomes acute and acute, and this is a pure tone. Let's go to the last of this elementary signal, which is the complex exponential. So this plane is where you can represent the complex numbers. So a complex number can be seen like a real part and imaginary part, or a modulus, which is the distance from the origin and the phase. So the two representations are equivalent, and we have here both of them. And suppose you are now putting a phase which is a function of time. So you keep constant the distance from the origin, and you have a phase which is a function linear of the time. What happens is that this point along the time starts rotating on a circle because the modulus is constant, and you get a picture like this. So the complex number is changing position along a circle, and the number of cycles per second is proportional to f0, is equal to f0. If this is positive, you are rotating anti-clockwise. If this is negative, you are rotating in the other direction. And the real part and the imaginary part of this point projected on the real axis and on the imaginary axis, one is a cosinus and the other is a sinus. This kind of signal is called complex exponential. And we are here plotting one signal that has a period of 1 second, amplitude 3, and the initial phase pi/3. I want to show you also an example of the composition of a signal in complex exponentials. If you take a cosinus and you sum two complex exponentials, one rotating anti-clockwise, the other clockwise, the imaginary part will always cancel and the real part will double, so that the final number, the final function you have, the final signal, is always real and is plotted here in magenta, and this is a cosinus. So this is one example of how you can decompose a signal, in this case a cosinus, as a sum of complex exponentials. And this ends this lesson about elementary signals.